Hello everybody. Today we're going to go ahead and look at some more information on attraction forces. In the previous video you guys should have watched was on intermolecular forces. It's pretty much a review of honors chemistry. That's really where that video came from, was my honors chemistry video. But the idea was just to recap molecular polarity and how to determine intermolecular forces. I'm going to go over the bigger picture here, which is the overall thing called attraction forces. So there's a little bit more than just those intermolecular forces. So let's take a look here. All right, so when we're looking at substances in nature, the substances are held together by attraction forces. Everything in nature is held together by attraction forces. Your body's held together by different types of attraction forces, and the desks and tables and stuff that you don't, those are held together with a different type of attraction force. Hence why you don't stick to those and get, you move past them and become part of them. All right, so anyway, what I'm getting into here first is ionic bonding. So there's different types of attraction forces. Now, if we look at ionic compounds have these positive negative attraction forces, and I talked about this in the we've talked about this in the past when we talked about ionic bonding. We talked about this having a lattice structure and that there's a lattice energy here. So don't forget about lattice energy. And for lattice energy, we're going to use Coulomb's law for doing that, and that would be Q1, Q2 over R. So with the strength of the lattice structure, the strength that's holding this ionic system together is based on this equation where Q1 and 2 are the charges and R is the distance between them. So if you remember, we said that the higher the charges, the stronger the lattice energy, the stronger these ions are going to attract each other. R is the distance between them. So the further apart the ions get, the further away the center of the ions get, the weaker it is, because the higher this number, the lower the lattice energy. Okay, so we find that the smallest atoms or smallest ions and the highest charged ions are going to be the ones that have the strongest lattice energy. All right, so when we deal with ionic compounds, the entire structure, it's all positive negative attraction. The entire structure has its same type of bonding. It's all ionic bonding throughout the structure. There's no separation of a different type of charge or a different type of attraction force. Now over here we have a metal. Okay, so this would be what's referred to as metallic bonding. Okay, now with metallic bonding, what we have are, what's holding this together is the fact that you get these positive nuclei, or these positive atoms. I guess I shouldn't say nuclei because there are still electrons on here. These negative charges are electrons that are free to move around, and these would be the valence electrons that aren't held on so very tightly. So in the atom itself, there are still some core electrons in there in the nucleus, but they're staying in a position. So there's a bond that's holding these together. This is referred to technically as a non-directional covalent bond. I wouldn't worry too much about that part, but just keep in mind that the atoms are held rigidly together in this lattice, very similar to what we see over here. We're going to see in all of our solids, we're going to be talking about them being in a lattice. But the electrons, well, these electrons are now free to move throughout the solution. So we've got these electrons that are moving. I guess I shouldn't say solution, because it's a solid state, but these electrons are free to move. This is called the electron C model. Electron C model. And this is what holds the metals together. So you get the electron C model. All right, so the electrons are free. This is why metals will conduct electric current, why they conduct heat very well. It's because of the mobility of the electrons. So it's different from the ionic bonding because here they're held together by these somewhat covalent bond, and then the electrons are free to move throughout the entire solid structure. So we get two different materials: an ionic compound, typically a white solid, a metallic solid, based on the fact that we have these electrons that are free to move around. It's going to be silver, it's going to shine, it's going to reflect light. Why does it do that? Because of the moving of electrons. The electrons are free to move. They're going to bounce that energy back off, and I'm not going to get into the details there, but that's really why that happens. Now down here what I have is carbon, and this is looking at a different type of force that's holding together these particles. All right, so we had ionic bonding holding together ionic bonds, metallic bonding holding together metals. Now for carbon, which is a nonmetal, so this would be a nonmetal substance. Nonmetals are held together by covalent bonds. Okay, so we have here covalent bonds that are holding these together. So the bonds that are inside here are those covalent bonds. We have covalent bonds. And if you notice, very similar to this to the sodium iodide, to the ionic compound, the entire structure is made up of covalent bonds. So we get a remember, covalent bonds are really strong. Ionic bonds are really strong. So covalent bonds, by the way, tend to be a little bit stronger than ionic bonds. Not every covalent bond is stronger than ionic, but most of them are. So what you have here is very strong bonds held together, holding these carbon atoms together. Now this is considered diamond, and diamond is the strongest natural material. Why? Because it has these very strong covalent bonds, and it has this tetrahedral structure, which creates a very stable structure. So between the fact that we've got the strong covalent bond and the tetrahedral structure here, creates a very strong bonding. Now, keep in mind, when we talked about hybridization, this is sp3 hybridized carbons. So each of the carbons in here has an sp3 hybridization, which gives you the tetrahedral structure. Now, if we come over here and look at this substance that I have over here, this is graphite. Now, graphite is very similar to diamond in the sense that it's carbon atoms all together. So these are all carbon atoms. And again, the bond here is a covalent bond. So we get another covalent bond on our carbon. So it's held together with covalent bonds. Now the difference here is that the hybridization is not sp3, but it's sp2 hybridization. So that different hybridization gives us 1, 2, 3 covalent bonds. Over here, 1, 2, 3, 4. Remember, if you add up the exponents, it tells you how many bonding areas. Since I have three bonding areas, so therefore 3 covalent bonds. But in this area above and below, what I end up having is a 4th bond, and that's considered that pi bond. Remember, pi bonds are above and below, and those sigma bonds are the bonds that are in between the two atoms. So these would be all sigma bonds. There's no pi bonds in the diamond. In graphite, you have pi bonds above and below the internuclear axis, and you have sigma bonds in between the atoms. Okay. Again, this is reviewing a little bit too, by the way, so that's why I'm going through and explaining all this. This isn't necessarily important for this chapter, but I just want to kind of recap a little bit from earlier. So what you have are these sheets of graphite that hover above each other on these pi bonds. These are very weak, while the covalent bond that holds the atoms together is very strong. And that's why graphite is very slippery. You can kind of think about it as like sliding back and forth on this cushion of pi bonds that kind of acts as a lubricant between the two layers. And that's why we use graphite as a lock lubricant, and we use it on our pencils. As your pencil rubs across the paper, it rips off these layers of graphite. Alright, so let's get back to, so here we recap real quick. Ionic bonding, if you have it in an ionic compound, metals have metallic bonding. Anything that's non-metal, carbon, sulfur, phosphorus, I'm talking about just the elements by themselves, are going to be considered what are called covalent bonded substances. I'm going to get into the name of what these are in just a little bit. Alright, so as you saw in the last video, there's dipole substances. I'm not going to go too much into this. I want to get to the other stuff. So you got dipole substances. That's a substance that has a positive and a negative charge to it. Any molecule that is polar, very important that you go back and review Lewis structures, because you have to determine if something is polar or nonpolar. The type of attraction force that we're going to have here is a type of intermolecular force. Alright, so here we're dealing with molecules. Now we have a molecule here, such as water. Inside the water molecule is the type of bond that we call covalent bond. Between the water molecules is the intermolecular force. Now the intermolecular force is only really true for molecules. So this page really is talking about molecules here. So if my molecule is polar, then the attraction force is referred to as a dipole force. Alright, that's true for polar, but remember there's special cases where you have hydrogen bonded to nitrogen, oxygen, or fluorine. Those three elements, if there's hydrogens bonded to any of those three elements, then you have that hydrogen bonding that exists. So this would be considered hydrogen bonding. Again, it's the same idea. Positive, negative attraction force. Positive, negative attraction force is what's going to cause these two molecules to stick together. So molecules are a little bit more complex. In the last slide we just saw when we were dealing with elements, and ionic compounds. So those other ones, really it was the same force throughout the entire structure. When we deal with molecules, there's two different types of forces. There's the force in the molecule and between the molecules. Okay, so you have dipole-dipole between two polar molecules. If the polarity is extremely strong, that is hydrogens bonded to nitrogen, oxygen, or fluorine, you get hydrogen bonding. Down here is London dispersion. Again, if you want to recap this, go back and watch the other video, but the idea is just that you create these temporary dipoles, and again, you get this positive negative attraction for it. Again, this would be your London dispersion forces. This is only true for nonpolar molecules. All right, attraction forces can also occur. We're going to see this in the next chapter when we get on solutions. There's something called an ion-dipole force, and I didn't cover this in the last video. Okay, an ion-dipole force is when you have an ion, such as sodium or chloride, is attracted to something that has a dipole. Water is an example of something that has a dipole. Even though it's extremely strong hydrogen bonding dipole, and that actually makes it even better, but either way, it's still a dipolar molecule. Attracts the sodium ions and surrounds it, and then the anion is surrounded by the positive sides of the water molecule. So because of this, the attraction force I'm referring to is this attraction force here. This is our ion-dipole attraction force. Those two are attracting each other. Okay, so those are some attraction forces. So how do I know which attraction force to use? So the first thing you want to determine is if it's a compound or an element. Oops, I just realized I spelled that wrong. So we're looking for whether it's a compound or an element. If it's an element, well, then it's either going to be one of three types of elements. It's either going to be a metal, a nonmetal, or a noble gas. Okay, so the attraction force between metals is going to be that metallic bonding that we saw before. Okay, if it's a nonmetal, then we're going to say that it's covalent bonding. All right, so the type of force between, so an example of this would be copper, an example of this would be carbon. Okay, now if it's a noble gas, then it's going to be something like helium or argon. Okay, it's going to fall into the category of London dispersion forces. So that's what holds together helium and argons. So that's the attraction force that's there. Now, if it's a compound, you have to determine whether it's ionic or molecular. If it's ionic, then you're going to have ionic bonding. Not a big deal. If it's molecular, well, now you got to get into the fact that, well, wait, is the molecule polar or nonpolar? If it's nonpolar, your answer is London dispersion force. Examples of that would be H2, O2, pretty much, again, you can actually have HC4 or CH4. You could have carbon dioxide. Those are all examples. Now, by the way, H2, O2, NO2, those special diatomics that we talked about, these are not atoms. These are not elements, right? Not atoms or elements. These are molecules. These are molecules. So we got to keep in mind that these are molecular substances. So these are actually molecules, not elements on this side. So when we deal with H2O2, we got to think of those as actually, two hydrogens bonded together. That's not an atom or an element. That is a molecule. So keep that in mind. If it's a molecule and it's polar, well, then you got to watch for hydrogen. Is hydrogen bonded to fluorine, oxygen, or nitrogen? Okay, if it is, then you would say hydrogen bonding. So you could say, example, water, NH3, if I could write better, HF be another example. And then if it's just dipole, that would be something like SO2, something along the lines of HCl. So those would be examples of dipole attraction forces. Okay, so it's a nice little flow chart to help you figure out what attraction force to use.